So hello and welcome back. This is the third and final part of my presentation on a compactness theorem in the moduli space of singular constant Q-curvature metrics. So there are three parts to this talk. I will describe the setup for our proof. I will describe some a priori upper bounds for solutions, and this will allow us to extract a convergent subsequence of the conformal factors. And finally, I will show that this limit function is actually a valid conformal factor. So we're going to begin by recalling the statement of the main theorem. Remember that I have a moduli space. The unmarked moduli space is the moduli space of singular constant Q-curvature metrics with positive scalar curvature, where the singular set is some collection of k distinct points on the sphere. And this moduli space has the Gromov-Hausdorff topology. The sets I will choose satisfy the property that the spherical distances between distinct punctures remains bounded away from zero, and the asymptotic neck sizes, which we've described previously, the asymptotic neck sizes also remain bounded away from zero. And the statement of the theorem says that this set is sequentially compact. So to prove this, I will start with a sequence of metrics in my moduli space. I write my GI as my conformal factor ui to the power of 4 over n minus 4 times the round metric. And I'm going to write the singular sets capital lambda I as some collection of points p1i through pki. And what I would like to prove is that there's a sequence of subsequence of conformal factors which converges uniformly, and that this limit conformal factor actually gives you an admissible metric. So as a first simplification, we can actually pass to a subsequence such that the limit sets all converge. So this is because each of my singular sets, capital lambda I, lies in a fixed compact set in the k-fold product of the n sphere, where the distance between two distinct points is at least delta 1. So this is a nice compact set, therefore I can pass to a subsequence such that pji converges to some pj bar. And I'm going to denote this limit singular set as capital lambda bar. It's going to be convenient for some of the later analysis to choose a specific compact exhaustion of Sn, the n sphere minus this limit singular set. And this compact exhaustion is going to be for each natural number n, I choose all of the points q such that the distance between q and any puncture point pj bar is at least 2 to the power minus m. And one of the convenient things about, and in fact, this is going to be true of pretty much any compact exhaustion you choose, but it's a little bit easier to do the analysis on a concrete compact exhaustion. So the thing that's a little bit convenient about this is that for any fixed m, when I is sufficiently large, the function ui is actually smooth on this compact set km. Okay, so I'm going to discuss a priori bounds. So what is our a priori bound? An a priori upper bound. So the theorem is the following. If I have dimension at least 5 and a proper closed subset capital lambda in the n sphere, and G is a conformally flat metric, conformal to the round metric, which is complete on Sn minus this set capital lambda. I want the scalar curvature to be positive, and I want the Q curvature to be equal to this constant. Then there exists a constant C, which depends only on the dimension n, such that U, my conformal factor U, is less than or equal to C times distance to the singular set to the power 4 minus n over 2. So I can write this, in other words, by saying U times distance to the singular set to the power n minus 4 over 2 is uniformly bounded by a constant which depends only on the dimension. Jin and Shang prove a very similar upper bound. Ours is only a little bit slightly stronger because our constant does not depend on anything other than dimension. Okay, the proof of this a priori upper bound is actually a fairly standard blow-up argument. So I'll go through most of it fairly quickly. You can find similar blow-up arguments many places in geometric analysis. And the idea is the following. I suppose the upper bound does not hold. So first I'm going to construct an auxiliary function f. If I choose some point x0, which does not lie in the singular set, and a sufficiently small rho, then I define the function f of x is rho minus distance to x0, all to the power n minus 4 over 2, all times u. So if I happen to choose rho is equal to 1/2 the distance to the singular set, and I evaluate my f at x0, I find essentially the thing that I want to show is uniformly bounded from above. And the idea is, if there does not exist such a uniform upper bound, I can derive a contradiction. And I derive a contradiction by rescaling my solutions. So let's go ahead and do that. If there does not exist a uniform C, depending only on dimension n, then I can choose singular sets, capital lambda I, and conformal factors ui, base points x0 I, and radii rho I, such that this mi, which is the supremum of f over the appropriate ball, goes to infinity. Now I rescale my solution to get my wi of y is lambda I to this power times u of lambda I y. This is now defined on a Euclidean ball. And the radii of these Euclidean balls become very, very large. And the other thing is that the other thing I should remark is that by the scaling law for the Paneitz operator, these wi's actually satisfy the same equation that the ui's do. So now I take a limit. So I can take a limit because actually each of these wi's is bounded by hypothesis. By the scaling, I know each of these wi's is bounded by 2 to the power n minus 4 over 2. So in the limit, what do I obtain? I obtain an entire function defined on all of Rn, which is positive, and it satisfies u bar of 0 is the supremum of u bar is equal to 2 to the power n minus 4 over 2, and also the bi-Laplacian of w bar is equal to this dimensional constant times w bar to the n minus 4 over 2. So by the classification theorem of Lin, so C.S. Lin classified all of these possible solutions, and he showed that this one, by our normalization, actually has to be the standard spherical bubble. And what does that tell me about the geometry of these metrics GI, which is UI to the power 4 over n minus 4 over n minus 4 times the round metric? This tells me that large coordinate spheres with respect to these metrics are geodesically concave. But a theorem of Alice Chang and Z.C. Han and Paul Yang shows that these spheres are always geodesically convex. So I get a contradiction. Right. So now, now that I have my uniform a priori bound, I can restrict to each compact set Km, and I can use the Azalea-Ascoli theorem to extract a convergent subsequence. And these sets Km now form a compact exhaustion. So my limit function U bar is something I can take to be defined on all of Sn minus the limit singular set lambda bar. Okay, so this is now essentially the final part of the proof. We would like to show that this G bar, which is U bar to the power 4 over n minus 4 times the round metric, is actually a valid conformal metric, which means I must show that this U bar cannot vanish. So a priori, I could have points where the UIs converge to 0. I don't want to allow that. So this is the part of the proof where the Pohozaev invariants come in, and the next size bound, the fact that the next sizes are all bounded away from 0, that becomes important in this part of the proof. So suppose this G bar is not a valid metric, then there must be a point Q in the n sphere minus my limit singular set such that U bar of Q is equal to 0. Now I let epsilon I be UI of Q. And this is a sequence of numbers which goes to 0. And I rescale my solutions again, just multiply by 1 over epsilon. And by the scaling law for the Paneitz operator, now my Paneitz operator applied to the Wi is this particular power of epsilon. I have some fixed power of epsilon I times the dimensional constant times Wi to the power n plus 4 over n minus 4. And by our normalization, we know that the Wi's of this fixed point Q are all 1. Okay, so I have a priori estimates, and I also have a Harnack type inequality. So then I get convergence Wi going to some W bar on my compact sets Km. So in the limit, I have now a function W bar defined on the n sphere minus my limit singular set. And this time it satisfies P of the Paneitz operator applied to W bar equals 0 because these epsilon i's all go to 0. So what I obtain here is just 0 on the right-hand side. And what does this mean? This means that my limit function W bar must actually be a sum of Green's functions with poles at the puncture points. Okay, and we'll write down in a second an expansion for the Green's functions. By our normalization, so recall our normalization is that each Wi at my fixed Q is equal to 1. So one of these coefficients alpha j is non-zero. I only need one non-trivial coefficient. Let's go ahead and assume that alpha 1 is non-zero. Okay, what do the Green's functions look like? Well, the Green's function for the Paneitz operator on the sphere. A theorem of Gursky and Malchiodi shows that this Green's function actually has a very nice expansion. I have a dimensional constant here. I have distance to the pole of the Green's function to the power 4 minus n, and then the remainder term is bounded near p. Now at this point, we like to center our coordinates on this fixed puncture point P1 bar, and we're going to apply the cylindrical transformation to a punctured ball centered at P1 bar. And then I obtain these functions. So I have VI is my cylindrical transformation of UI. So I have to be a little bit careful because I have to remember that my UIs are not conformal to the flat metric, they're conformal to the round metric. So I have to additionally put a factor of the spherical conformal factor in here. And if I go through the definition, I see that, recall what the definition of U sphere is. I see that this VI of t is cost to the power 4 minus n over 2 times ui of e to the minus t theta. And similarly, I'm going to let zi be the same cylindrical transformation applied to wi, and this is the same thing as just writing down 1 over epsilon I times vi. Now, all of these functions, these vi's and these zi's, they're well defined for t greater than some fixed t1. And they all satisfy nice equations. The vi's satisfy an equation which looks like the cylindrical Paneitz applied to vi is a fixed dimensional constant times vi to the n plus 4 over n minus 4. And because of my scaling laws, the zi's satisfy an equation which looks like Paneitz operator applied to zi is epsilon I to the power 8 over n minus 4 times my fixed dimensional constant times zi to the n plus 4 over n minus 4. I also have my radial Pohozaev invariance, and this is where I apply my radial Pohozaev invariance. If I look at the integral over any constant t slice of my Hamiltonian applied to vi, this integral does not depend on t at all. Similarly, if I look at the integral over any constant t slice of the cylindrical Hamiltonian applied to zi plus this epsilon I times zi to this power, this integral also does not depend on t at all. And the important thing here is that now I can extract a limit of this bottom Pohozaev invariant. And when I do that, I see that this term with the higher power of zi goes away. It goes to 0 because these epsilon i's all go to 0. So that's what we're going to do in a second. By the convergence that the wi's go to a sum of Green's functions, the zi's all go to some z bar. The expansion I have for w bar is that near the point p1 bar, it looks like alpha 1 times this divided by this dimensional factor times length of x to the power 4 minus n plus some bounded remainder term. And then if I transfer this asymptotic expansion over to z bar, I find this is an asymptotic expansion for t very large. I find that z bar is equal to a constant, alpha 1 divided by a dimensional constant, plus a remainder term that decays exponentially. So now I put my expansion for this z bar into this guy. And what do I find? I see that my radial Pohozaev invariant for the zi's converge to the integral of the cylindrical Hamiltonian applied to z bar, but now by the expansion I wrote down here, that's just some constant, some negative constant, plus a remainder term that decays exponentially. And now I let t become very, very large, and I see that this remainder term actually disappears. This goes away. So all I am left with is this fixed negative constant. And if I backtrack and see what this means for the original radial Pohozaev invariance of these original GIs at the puncture point P1I, well, that is the integral over a constant t slice of the Hamiltonian applied to VI. But then when I substitute what that is, I find epsilon I squared times the cylindrical Hamiltonian of Zi plus epsilon to a power larger than 2, epsilon I to the power 2n over n minus 4, times this factor. And what do I see? This term goes to 0. And this term will also go to 0 because this term here will converge to this. So what I obtain is essentially epsilon I times this guy here. That goes to 0. So what have I just shown? I've just shown that in this case, the radial Pohozaev invariants of GI at P1I have to converge to 0, but by our characterization of the radial Pohozaev invariance, this means that the Delaunay next sizes epsilon 1I at GI of GI at the puncture points P1I all converge to 0. This finally contradicts the hypothesis that all of the next sizes, all of the Delaunay next sizes remain bounded away from 0. And it completes the proof. So we've just shown actually that my limit function ui bar that I constructed from this subsequence is a valid conformal factor. It's a valid metric on this on Sn minus this limit singular set. So the final detail we have to show is that this limit metric is complete on Sn on this n sphere minus this capital lambda bar. So suppose this limit metric were not complete, then the radial Pohozaev invariant for one of the limit metric at one of the limit puncture points must be 0, but that in turn implies the radial Pohozaev invariant of GI at PJI must converge to 0. And that in turn implies that the Delaunay next sizes of GI at the puncture point PJI have to go to 0, but that contradicts the fact that the Delaunay necks are all bounded away from 0. And that finally completes the proof of our theorem. So thank you very much for listening. Thank you for your attention. And if you have questions, I look forward to hearing from you, reading whatever you have to say at this email address. It's jesse.ratzkin@mathematik.uni-würzburg.de. Bye.